Okay, today we're going to talk about optimization, and this actually is 4.2, so it goes before the 4.3 video that I made. So he shows you a function that you graphed in class, and he says, how are we going to find the inflection point? So an inflection point on the graph is a point where its concavity changes, so from concave up to concave down, okay? Concave down to concave up, so somewhere in here. So right now I think we have two inflection points on this graph. Okay, so let's see how we find them. So you find the inflection points in the following way. Take the second derivative of the function, set it equal to 0, and solve. Right? And then you need to test it, because sometimes you'll find something that truly isn't an inflection point. So let's first take we have to take this, and we're going to first take our first derivative, because we need to do that to get the second. So this becomes 4x to the third minus 12x squared. And my second should be 12x squared minus 24x. So I have now my second derivative. I'm going to set it equal to 0. Trying to make sure. All right, let's set this equal to 0 and solve. So basically what I could do is I could factor out a 12x, right? And I'd be left with x minus 2 equal to 0. So 12x equals 0, so x equals 0. X minus 2 equals 0, so x equals 2. So I'm going to test both of these points, x equals 0 and x equals 2. What I do is I need to make sure the second derivative changes sign, right? If the results are positive on one side and negative on the other, or vice versa, then it's then it's an actual inflection point. So let's test something like x equals 0.1 and x equals negative 0.1. All right, we're going to plug those into this second derivative. Okay, so if I plug in 0.1 squared times 12 minus 12 times 0.1, this is a negative 1.08. Let's look at this one. We'll put a negative 0.1 in. So if I put this in, I go negative 0.1 squared times 12 minus 24 times a 0.1, which is plus 24 times 0.1. And this is a positive. So yes, and it's an inflection point. Let's try 2. I'm going to check x equals 1.9 and x equals 2.1. So 1.9 squared times 12 minus that 24 times 1.9 gives me a negative answer. Let's check this one. 2.1 squared times 12 minus 24 times 2.1. That gives me a 2.52. Let me go up here. Yeah, this was negative. So yes, that's an inflection point. As long as it changed signs from concave up to concave down or the other way around, it changes concavity, okay? He doesn't give you the vice versa here, but he should, okay? All right, let's look here. How do we find global extrema? We found local extrema, right, by using the first derivative and setting equal to 0, but now global, we need to check our endpoints. So on a closed interval, we actually have endpoints here that we can check. So it says find the critical points of f in the interval by f prime. So you have to evaluate the critical point, get a value with the graph, the original graph, because you're trying to find out where the original graph is high or low, right? But you use f prime to find the critical points, the first derivative. So let's try one. It says find the global extrema for this particular function. So the first derivative is going to help me find my critical point. So f prime of x is 4x to the third minus 3x squared. Let's set that equal to 0. If I pull out an x squared, I have 4x minus 3 equals 0. Set these equal to 0, and I get x equals 0, or x equals 3 over 4. All right, let's take the function at f equals 0, and we get 0. It's probably not, I don't know, we'll see. Let's take the function at 0.75. We're evaluating it here, and we get something like negative 0.1055. Now I need to check my endpoints. So if I go back, oh, here's my closed interval. I need to check the endpoints. I have values for the critical points, but let's take the function. This is the original function, right? We must test for global max and min in f of x, not the derivatives. So f of negative 1 happens to be 2, and f of 2 happens to be 8. So let's see. The lowest number is this, and the highest number is this. So f, or I should say, x equals 2 is my global max, because it's over the entire interval, and x equals 0.75 is my global minimum over the entire interval. It'll be a little different in a bit, but let's do another example. Here, we run a small furniture business, and you sign a deal with a customer to deliver between 300 and 400 chairs. So guess what? My interval is 300 to 400, isn't it? All right. You have determined that the revenue for this order is given by this equation, where x is the number of chairs ordered in excess of 300. What are the largest and smallest revenues your company can make? Keep in mind, if x is the number in excess of 300, we need to revise this closed interval to be 0 and 100. Okay? So we're going to take r, here it's 2700 plus 15x minus 0.25 x squared. All right, we need to take the derivative, don't we? We're trying to find the largest and smallest revenues. Really, those are global max and global min, right? Global max and min. Well, to find the critical points, we have to take the first derivative, which this goes away, and we end up with 15 minus 0.5x. All right, let's set that equal to 0. 15 equals 0.5x. X equals 30. So we found one critical point. So we need to test the original function. I'm going to say r at 30, and then we need to test r at 0, and we need to test r at 100. I've already done the math here, but r at 30 gives us a revenue. I must be in dollars. They really didn't tell us. R at 0 gives us a revenue 27,000, and r at 100 gives us 26,000. So now we determine our global max and min, right? Because they want to know the largest and the smallest revenues so they can plan. So here's the smallest possible revenue. So that's our global min. Here's the largest possible revenue. So it's our global max. Okay? Now, we just found the global max and min on a closed interval. So we had actual edges or ends of the interval to test. Now we're going to talk about finding it on an open interval. So it says, find the values of the critical point just like we have. Compare the values in 1 with the values as x approaches the endpoints. If the larger value is attained at the critical point, it is a global max. If the smallest value occurs at the critical point, it's the global min. Otherwise, neither exists. So let's try this. The function in this sample is f of x equals x e to the minus x. All right, we got to use our product rule, don't we? So our product rule is f prime g plus f g prime. So the derivative of x is just 1, and then just g, right? Plus x times the derivative of g. Well, the derivative of this is e to the minus x times the derivative of this, which is negative 1. So this is e to the negative x minus x e to the negative x. Set that equal to 0. Let's see what we get. All right, I'm going to factor out e to the negative x, and I'm left with 1 minus x equals 0. Well, this e to the negative x function never hits 0. If you graphed it on your calculator, you can't find a point where it's 0. But here, x equals 1. So I'm going to evaluate the function at 1. Okay? If I come over here for a second, f of 1, which is 1 e to the negative 1, equals 0.3679. Okay? Now, as we approach our endpoints here, so we're approaching, this is an open interval. Let's see what this open interval is. I think it's 0 to infinity, right? So let's take our function x e to the negative x. See, we can't do an e to the 0. It does not exist. Let me look. I could be wrong. Hang on. Because this is 1 over. It's not e to the 0 doesn't exist, but e to the negative 0 doesn't exist, right? Because we can't have a 0 in the denominator. So let's say what's happening as we get really, really small. Okay, I'm going to take a really small number. Let's take 0.001. Okay, so if we look at that, it's, I should do this to the x, isn't it? So I'm going to say e, clear. Okay. All right. E raised, having a tough time, raised to the 0.001. I want the reciprocal of that. So there's my, I'm having a tough time here. Okay, I'm going to say 1 divided by second e raised to the 0.001. All right, this number right here is 0.999. Then I'm going to multiply it by 0.001. So the function here is pretty small, 9.99 times 10 to the negative 4th. Okay? Now, as this function, and we can look at this function and see what's going on. Let's see. This is small, and this function is going to be small as it approaches. We basically know, based on this, that my f of 1, this here is my global max. Right? When you just look at the function, if I evaluate it here, it's very small. If I evaluate it as it heads to infinity, it's very small. So I do have a global max, but I do not have a global min, because it says if the smallest, well, he says if the smallest value occurs at a critical point, it's a global min. Otherwise, the global min doesn't exist. Because I don't have a global min as a critical point. These don't matter. I don't have a global min. So this is my global max. So these are good to remember, that if you have a closed interval Oh, it's going to end now. Thanks.